So welcome everybody. It's a pleasure to welcome today, or to have today as a presenter, Anthea Fantina. She's a theoretician. She currently works at GANIL, where she's there since 2015 as a CNRS researcher. And Anthea, she made her thesis at the IPN Orsay, so what is now IGC Lab. It was a co-direction between IPN Orsay and Milan University, and she finished her thesis in 2010. And then she did a postdoc at the University of Bruxelles with Nicolas Chamel and Stéphane Gorielli. And then after this, she got the CNRS position, and her main interest and her specialty is the theoretical description of dense matter I hear some people. Well, in compact objects. And today she will talk about probing the properties of dense matter with neutron stars. So please, Anthea.
Thank you very much. Thank you very much for the invitation, and thank you very much for coming to this webinar. Indeed, today I will address how we can probe the properties of dense matter with neutron stars. So I will give a brief introduction on neutron star physics, and I will particularly focus on the modeling of the equation of state and how we can get constraints from nuclear physics specifically. And then I will show you how we can relate the equation of state to the prediction of neutron star properties, and possibly how we can now or in the future discriminate between models. And in the last part of my talk, I will actually address I will spend a few words describing proto-neutron stars, so neutron star at finite temperature, before concluding. So for this talk, I will speak about what I call bit equilibrated matter. This means that I will assume that weak processes are in equilibrium. This is true for cold mature neutron star, but also for proto-neutron stars after, say, tens of seconds or minutes after their formation. So first of all, what's a neutron star? So a neutron star is the remnant of supernova explosion. So the progenitor in this mass versus evolution time diagram are situated here. These are masses with more than 8 to 10 solar masses that at the end of their life, they configure themselves as an onion-like structure. We have an ion core and a lighter element as we go towards the surface. So when we have this kind of configuration, the ion core collapses, bounce, and eventually the shock wave eject the outer layers of the stars, leaving us with a compact remnant, which can be a neutron star, or typically for more massive progenitor, a black hole. So when we actually observe neutron stars, so we observe them since the late 60s. The first observation was actually done by a PhD student, Jocelyn Bell. She was looking on radio sources, and she actually discovered a very, very regular source with a very specific period. And they didn't really know what it was. That's why at the beginning they called this little green man, but it is actually been identified as a pulsar, which means a rotating neutron star. And indeed, this is how we observe most of them. We have a beam, so it's like a lighthouse effect. When the beam is towards us, we see it. And we can actually now know more than 3,000 pulsars, either in binary system, you see them here, or isolated. And we can precisely measure their period, so their rotational frequencies, and even the period derivative, so the variation of the period with time. And so, and some of them actually have strong magnetic field. These are here, they're called magnetars. So we don't just observe their period, but we can also observe many other properties of neutron stars. So first of all, masses. We see here a collection of them. Some are very, very precisely measured. You see here the error bar is very small. So you see these are objects between 1 and 2 solar masses, typically 1.4. But we can also have some so-called massive neutron stars that have been observed with 2 solar masses. Then we observe radii. This is a recent measurement, and we can see that these are city-sized objects between 10 and 15 kilometers, more or less. and which means that these objects are very, very dense, as I will show you in the following. Then we also observe, well, I say observe in a quite loose way, because these observations of the magnetic fields as for the radii are not direct. These are inferred from observation. Particularly, the magnetic field is often inferred from the PP dot diagram I showed you just in the slide before this one. And you see some have a very high magnetic field. Or very recently, measurement of the tidal deformability has also been obtained. So tidal deformability is a property for which, if we have two neutron stars that are coalescing, when they are close to each other, they feel each other. So it's like the Earth and the Moon, and there are tidal effects. And this deformation due to tidal effect is called tidal deformability. And there has been one measurement through gravitational waves observation from this object, GW 170817. So as I said, most of these observations like magnetic field are inferred, so they're not, they're model dependent, but still. And to convince you that we really probe extreme conditions in these objects, I show here a phase diagram where we see temperature versus density versus, this is the isospin asymmetry, so neutron-proton asymmetry. And we see that neutron stars live basically here. Cold objects are, have low temperatures, but still in their interior, they span a very many order of magnitude. So we go from an outer crust with nuclei and electrons, an inner crust, and then we go to a core where at the beginning we just have no more nuclei, so neutron, protons, electrons, eventually muons, and then in the very center we really don't know. We could have quark, iprons, say exotic particles. And as you can see here, the interior of these objects can reach several times, even 10 times, the density that we can find inside an atomic nucleus. So these are very extreme objects. We can explore many properties like, there is the question of, do exist exotic particles in these objects? Is there superfluidity in neutron stars? How to do with so high magnetic field? I will not discuss these topics in the talk, but still keep in mind. And this means that not all conditions can be probed currently in terrestrial laboratories. So we need to rely on theoretical models. And unfortunately, the connection between the experiments that we can have from nuclear physics and the astrophysical observations, so the predictions, is not a direct connection. And we need a theory on two levels. First of all, we need theory from the nuclear physics point of view, because we need to connect our knowledge from experiments to what we call the equation of state, rates, and so on, which are inputs to the astrophysical simulation that can predict ultimately astrophysical observable. So it's like two layers of theory. And I will now show you this connection here. So how from the equation of state, we can go and predict astrophysical observation. And this is what I will address just in the slides after. So how to do this? So think about a neutron star that is static, is mature, is cold. And so to find its structure is basically a problem of hydrostatic equilibrium. And you can recognize here the hydrostatic equilibrium in Newtonian gravity. And then you have some corrections that are due to general relativity. So this is the so-called Tolman-Oppenheimer-Volkov equation, is hydrostatic equilibrium in general relativity. And how do you do? Well, basically, you have to counterbalance. If the system is static, you counterbalance the gravity with the pressure of matter. And so you see here that the only ingredient that you need here is the pressure as a function of radius. So it's more, of course, more pressure in the center, less on the outskirts, and the same, more density in the center, less on the outskirts. So you need a relationship between the pressure and the radius, or equivalent pressure density. And so which means that to solve this equation, you have to integrate, and only the equation of state is needed, at least for static properties. And this means that for each central density, which is a parameter in the problem, you integrate this equation and you find the global radius and the global mass of the stars. And this is great because it means that general relativity imposes a direct correspondence between the equation of state, which is here, and the so-called mass-radius relationship. So each point on this curve represent a different central density. So this is a family of equation of state. A family of neutron stars. Two different equation of states would predict two different mass-radius relationships. And this is the same with the tidal deformability. Here I had two different equation of state, two mass-radius relationship. Here I have four equation of state, four different relation between the tidal deformability and the mass of the star. So that's perfect, that's great. Then you can say, I can do reverse engineering. And if I have a measure of lambda m, radius m, I can trace back to the equation of state. Actually, keep in mind this question because you will be able to answer in a few slides. What I can anticipate is that this is not at all a trivial problem. And the reason being, one of the reasons being, is that the equation of state is model dependent. So how to build this equation of state that we need to predict observable? Let's start from the outer part of the neutron star, from the crust. So this is this part here. You have initially nuclei immersed in a gas of electrons. And then in the inner crust, you also have some free neutrons that drip out of nuclei. And then at the bottom of the inner crust, you can also have deformed nuclei. These are usually called pasta phases, so they are really very deformed clusters. And typically what people do is they model the crust, dividing it into identical cells that are called Wigner-Seitz cells. So to calculate the equation of state, if you think that the neutron star is cold, which means that the temperature is below the Fermi temperature, everything is at equilibrium. And therefore, you can assume that for each layer of the star, you have one typical nuclei, of course, with the gas of the electrons. And then you just minimize the energy of the system, which is very easy to say, but as I will show you, not very easy to do. And I've stopped a bit on the crust because despite is only 1% of the mass of the neutron star, it's actually important for different phenomena like glitches or all of what is crustal properties. So let's try to do this job, so minimize the energy and see what are the predictions for the equation of state. So let's start from the outer crust. This is, say, a few hundred meters at the outer part. You see here the composition, so the neutron and proton number of the nuclei in the crust, calculated within some more microscopic models. So this is our Trifok-Bogoliubov model in green. And the lines are models within a compressible liquid drop model. So you can see here that there is an imprint of shell structure when you use macroscopic model, and that there is a dependence on the prediction on the many-body method, because if you don't use shell effect, like in this case, you see that the trend is okay, but you miss the correct composition. Now, for the equation of state, which is this one, relation between pressure and density, you can see that I can use different model, different functional, but this is actually relatively well constrained. If you look at the scale, there's not much of an uncertainty. Now, the problem gets more complex if we go through the inner crust. Why? Because in the inner crust, as I told you before, we just don't have nuclei and electrons, but we also have free neutron gas. And this means that we have to be able to model a neutron gas, which means interacting nucleons in a dense medium. And you can do it in a different way. Typically, I show you here three methods with which you do this from an increasing complexity. So you can do this within a compressible liquid drop model picture. This means that within your Wigner-Seitz cell I showed you before, this is your nucleus, this is your gas, and you actually artificially decouple the cluster from the gas. Then you can do things a bit better and give a surface to your nucleus, but still it's like one of the simplest model, but one of the most used because of its simplicity actually. Then you can do Thomas Fermi calculation, where you actually do not artificially distinguish nucleons inside and outside your cluster, so everything is treated consistently, and you typically impose the density profiles. So these in this Wigner-Seitz cell for two densities are neutron and proton profiles. And then you can go to full quantum calculation, which are the most complex, like Trifok-Bogoliubov. This I show the results of a seminal paper in this respect. No matter what you do, it's a variational problem, which means that you have to choose your variational variable. It can be the wave function, it can be the A and Z of your cluster, the dimension of your, the volume of your cell, and so on, but it's a variational problem. You minimize the system and you get your composition and the equation of state. And so still, as in the outer crust, we do have a dependence on the many-body method. This is the proton number in the inner crust. And you can see here, this is Thomas Fermi calculation with shell correction. So you see here the shell effects for different models. And you see here the results where there are no shell correction. So this is extended Thomas Fermi. So you, again, trend is okay, but yeah, there is a dependence on the result on the many-body method. And for the equation of state, we have also a model dependency in the functional. You use different functional, look at the scale now, it's not at all like before, you have order of magnitude difference. So the inner crust is here, and you see that you start having dependence in the functional. So if we go to the core, this is even worse because the spread is even larger. For the core, at least before the appearance of exotic particle, you can use either ab initio approaches to describe the system of protons, neutrons, electrons, eventually muons, or you can use more phenomenological models like energy density functional approaches. And you see here an example. Here you have some prediction for SCRM of the pressure versus energy density. Then you have here some relativistic mean field of microscopic model. And you see here that the spread is very big. And another way to see this is to look at this pressure versus density. So the equation of state in the core with many models, as you can see here, is order of magnitude spread. So the uncertainty in the functional is large, also because functionals are typically fitted, have parameters fitted on properties of nuclei and typically saturation density. Here we are extrapolating at few times saturation density. So really the model dependence counts. And then there is a problem, in the inner core, we do expect additional particle. Here is an example of 3 equation of state with quarks. So as you can see, if we account also for that, the spread in the prediction increases a lot. And as for additional particle, actually, the problem is not yet pinned down because the role of these exotic degrees of freedom is not really clear. Here is an example of a mass-reduced relationship obtained with the nucleonic equation of state, and here with the equation of state with iprons. So you can see here, if you add iprons, typically your maximum mass decreases because your equation of state softens, and therefore you have less pressure, you can sustain less mass. On the other hand, for quarks, it's not clear at all. Let's focus on only a few of these curves. Let's see the red one. The red one is nucleonic model. And then this black one is with quark, but also this black one is quark under 2 different hypotheses. So you can see that sometimes you have softening or sometimes stiffening of the equation of state. So really the role of the quark is not yet clear. And you can also have what in the literature is called masquerade effect, which means that 2 different equations of state with different underlying hypotheses for the composition leads to very similar prediction for masses and radii or for the tidal deformability. For example, look at this one, this is nucleonic, and this green one is an hybrid with quark. So if you remember my question a few slides ago, are we able to trace back the composition if we measure something here? You can answer and say that this is not tricky at all because we have error bars, and so this masquerade effect actually gets things very complex, and no, it's not always easy to trace back to the equation of state. So to, let's say, disentangle this problem of the composition at high density, what people also do is to use the so-called agnostic approaches. This means that for the high density part of the equation of state, they assume that the equation of state is either polytropes or sound of speed models, or you can have non-parameterized equation of state like Gaussian process, like these examples here. Here is a polytropic, here is a spectral and Gaussian processes that are typically conditioned from astrophysical observation. It means that you have an observation and then you try to reduce your uncertainty in the equation of state using the observation. This is great, it's very powerful because these models, there's no underlying hypothesis except for physically reasonable ones, like the equation of state has to be causal, you have to have stability, and so on, but there's no hypothesis on the composition. On the other hand, typically, since there is no nuclear physics behind, they use one only crust, and I showed you that actually there are model dependencies in the crust, so the uncertainties are underestimated in the equation of state. And then what about nuclear physics? We are nuclear physicists, we would like to actually have nuclear physics informed model. With this one, there is no way to know the composition. So I will try now to explain you this part of the diagram, this left part, so how to connect to have nuclear physics informed model, and how this can, what's the effect on the predicted observables. So typically the connection between the equation of state and, say, information that we can have through experiments is done through what are called the nuclear matter parameters. So typically what is done is that in infinite matter, you expand in a Taylor expansion in density and asymmetry around saturation density. Okay, here is a parabolic approximation we can discuss, but okay, let's assume you do this expansion, and then the coefficient of this expansion are directly related to what are called nuclear matter parameters. And this is the energy at saturation, the minus 16 MeV, this is the compressibility, this is the symmetry energy and the slope and so on. And so if we look at what is predicted by theory, well, for this symmetry energy slope and symmetry energy coefficient, okay, there is a bit of spread here, here a bit more, but okay, it's not so bad. But then if we go to what we call the high order parameter, so Q and following, this is absolutely unconstrained. You see that the spread here is huge. So the question is how we can get constraint on this parameter and therefore on the equation of state, at least from nuclear physics. So there are two ways of doing this, of course, to measure nuclear properties. I won't discuss all of them, but I will just show you some example. Or we have ab initio calculation. This is an example of the pressure for symmetric matter, so equal number of neutrons and protons, as a function of density, as extracted from ab initio calculation, the blue band, or from different experiments, the color band. And this is typically constrained, what I call the low order parameter, so the low density sector, we can see it here. The high density sector is typically more constrained by astrophysics, but for nuclear physics, we go until, say, twice saturation density. You can extrapolate here a bit more, but typically it's up to 2 saturation density. And so, how to do that? So, from the ab initio calculation point of view, actually, these are very good in constrained properties of pure neutron matter. Neutron star is a very neutron-rich object. It's not pure neutron matter, but still there are a lot of neutrons. So, ab initio calculation, like effective field theory, are very good in prediction for the equation of state of pure neutron matter. And you see here a collection of these calculations. These are effective field theory model, this is the Gandolfi's Monte Carlo model. And you see that, say, they agree up to, say, 1.5 saturation density. So these are actually very good benchmark for more phenomenological models that I show here in lines. Some clearly do not agree, but I mean, they can be benchmarked for a phenomenological model. On the other hand, in the symmetric sector, this is less clear because for symmetric matter, the uncertainties are larger, the saturation point is trickier to obtain, and therefore this is less constraining from for at least for the properties of symmetric matter. But for symmetric matter, we do have experiments. And these I will show you just some example. For example, for pure symmetric, for symmetric matter, constraints on the equation of state, so P versus N, can be obtained by different experiments. This is an example with chaos or flow data. We can have information from the giant monopole resonances, so collective thing in nuclei. Of course, this is not unambiguous because the giant monopole resonance actually is connected with the compressibility in nuclei, and then you have to have a way to extract to the compressibility of infinite matter, but still, okay, we can have some constraint. And as you can see here, is typically on the more symmetric sector. Another example is, for example, constraint that you can have on the symmetry energy. Again, these are different experiments, IV ion collision, isobaric analog states, and so on. And so you see, you can have a band, and then you can compare with your models and see if your preferred models is in or out the constraints. And this is a collection of constraints on the slope of the symmetry energy versus the symmetry energy coefficient obtained from different studies, either dipole polarizability, heavy ion collision, skin, ab initio. This green one are ab initio calculation. And you see here results from PREX. So this is the neutron skin inlet 208, which point to quite high value of the symmetry energy parameter. However, so there could be some tension, right? And the constraints are not clear. However, this constraint has been inferred using a selected set of models. So there has been a more recent analysis from Reinhardt and collaboration. You see this cross here. This is the same measurement, but analyzed with a wider collection of models. Actually, there's even, I think, some no relativistic models. So things are not always clear, and these are not actually raw data. These are deduced constraints. So it's raw data combined with theoretical models. So it's, of course, these model dependence. We have them, they're super good, but they are model dependent. So one has to put a caveat on that. No matter, once one has such constraints, this can be incorporated to predict neutron star observable. And how you can do that is through Bayesian study. So the idea is that you explore many models, you vary this parameter, possibly independently one from each other, and then you build your posterior distribution. You can start with many models with flat prior. So say your the energy at saturation is between, say, -17 to -15. Your K, your compressibility is, I don't know, 200 to 300, and so on. And then you constrain, you apply filter to your prior. And so you condition your prior with knowledge from nuclear physics. Either can be nuclear masses, it can be this low density calculation that I showed you, very powerful for pure neutron matter, or you can even use symmetric matter. And then if you want, of course, we have astrophysical observations, so you can also condition your model on, say, causality, so your equation of state has to be causal, from the fact that your equation of state has to predict neutron star with at least 2 solar masses, and so on. And doing that, one of the things you can answer is which one of these parameters are important for neutron star observable. And this is an example, at least for crustal properties. So look at the first row of the two panels here. This is the density and pressure of the crust-core transition. So this is the density here between the crust and the core. And this is important because it allows you to predict the crustal observable, like the moment of inertia. This is important for glitches. I haven't spoken about them, but this is observable. And as you can see here, the parameters that play the most role are not only the low order ones, so in this case, this L-sim, this slope of the symmetry energy, but you have the importance also on the high order parameter. You can see it here. So whatever constraint we can get from nuclear physics also on this high order parameter, that would help us to constrain the properties of the crust of the neutron star. Then what about the full equation of state? So you can start with your prior here. As I told you, is a flat non-informative prior. And then you can apply your condition nuclear physics information from low density. And of course, this, you see, it constrains your low density part, or high density part, astrophysics, of course, it constrains the astrophysics. And when you combine both, your actual uncertainty in the equation of state reduces a lot. Still, this is a log scale, so there are still plenty of uncertainties, but with respect to the prior is much smaller. And if we see what's the effect on the mass radius relationship, this is this blue shaded area at 1, 2, 3 sigma. So this is the prediction of the mass radius relationship for this kind of equation of state, and compared with some popular model, these are lines. So you see that too soft or too stiff are actually even discarded by observation. These are constraints from the gravitational wave. And these black lines are constraints from radius measurement from the nicer instrument. So you see that some popular models are not actually compatible with observation. And the other thing that one can say is that, I didn't tell you this before, but I tell you now, the only hypothesis that is done building this shaded area is that there are only nucleons in the neutron star. So I told you there can be additional particles, but for this posterior, we think that we assume that they are not. So, which means that the nucleonic hypothesis is indeed compatible with observation, which does not mean that additional particles do not exist in the neutron star. It simply means that current observations are not constraining enough to pin down the question. So, how to advance? How to advance? We can advance from the astrophysical point of view and the nuclear physics point of view. So from the astrophysical point of view, a great thing would be to have a smoking gun observation. This, I show you the tidal deformability, and these are for the two neutron stars, the merging neutron star. These are constraints from gravitational wave observation, this black line, and the blue is, again, prediction from a nucleonic model, imposing that the maximum mass of the neutron star is 1.97. Now, if tomorrow there is a measurement of a tidal for an object of 2.5 solar mass, and it is guaranteed that is a neutron star, because it has been speculated for this object, but not confirmed. So if one day it's guaranteed, then you see that my nucleonic hypothesis is clearly, is quite not compatible with what's inferred from observation. So there could be a strong indication of the presence of exotica in the neutron star. So the nucleonic hypothesis can actually be used as a null hypothesis. Another way is to have more precise and more numerous observation. For example, current constraint on the actually this is a combination of the tidal of the two objects, is between 0 and 800. And this you see the distribution. Now, if tomorrow I have an observation very precise, supposing here it's completely hypothetical, then you can see that I can constrain very much, because I can pin down which of the equation of state is good or not good. If I have, up to now, we have only one constraint, and this is rather loose. So more precise observation or more numerous. This is a prediction of the tidal deformability for a 1.4 solar masses or 2 as a function of observation. So the prior is here, and you see that as soon as I increase the observation, actually my distribution becomes very narrow and say reproduce two given models. And for this example, these two models are chosen, but say if I have many observations, that my prediction, I can really constrain my the equation of state model. The other point is having more sensitive detector. This is what is expected from the next generation, like ET. Indeed, if I have new generation detector, one can in principle expect to detect post-merger phase. Up to now, we measure till here. Post-merger phase can give actually indication of a phase transition in neutron star. So this would be really a great breakthrough. Now, from the nuclear physics point of view, we can have observation, or we can have more constraints. For example, these I show just examples, and I chose two. The first one is, if we have a reduced error bar in the neutron skin measurement, this again can help us constraining. This is the form factor of calcium-48 that is inferred in CREX, and this is on lead-208 by REX. So this is the actual measurement, and one can compare with observation and with the theoretical prediction, and indeed one hopes to pin down one has the smaller error bar to pin down the model. And one can even make some constraint on higher order parameters. This is an example. Actually, this ellipsoid is done using PREX measurement with a selected relativistic mean field model. And this conservative is done using more nuclear models. So you see there's a bit of tension. So if we can reduce this error bar, in principle, this could help. On the other hand, on the more higher density, we have heavy ion collision. For example, this is an example of results from the ADES collaboration. And this is the electricity of a proton versus the rapidity. And these are data compared with different predictions. These are the curves for different equation of state. So you see that things are quite sensitive to the equation of state. So indeed, this could help us constraining, say, the equation of state up to twice saturation density. So up to now, I've just spoken about cold neutron star, but I will spend the last, say, 5–10 minutes of my talk speaking about the neutron star at finite temperature. Unless there are quick questions so far. No? Then I go on. So neutron star, as I told you, they are born from core collapse supernovae. So these are objects that are born hot. Typically, they're born with, say, tens of MeV, and then they cool down up to 1, and then, say, kV, up to kV. But still, when they're born hot, which means that their temperature is typically above 1 MeV. So if we look at what happens, what we expect from statistical mechanics is that if we are at finite temperature, we do expect that for a given density and a given temperature, we have a distribution of nuclei. So we don't have just one nucleus per density, as I supposed until 2 slides ago, but we have an ensemble of nuclei. And this is shown here. This is the mass number of the nuclei that are expected in, for this density in the crust as a function of temperature. And let's focus on just the solid and the dotted curve. So the solid curve, this is the results with the, what I called one component approximation. So this is one nucleus per layer, say, of the neutron star. And this is instead nuclear statistical equilibrium calculation, so an ensemble of nuclei. And we see that at 0 temperature, the two, well, low temperature, the two predictions basically are identical. So what I told you before remains valid. But as soon as you go at finite temperature, you can see that the discrepancy is actually quite high, because this is almost 1.5 times more. So, so one needs really to consider an ensemble of nuclei, what I call multi-component plasma, in the crust of the star. So we go back to the outer layers and to the crust. And typically what is also assumed is that the neutron star freezes, so the composition is frozen at some temperature that is called the crystallization temperature. So you go from liquid to solid. And this is typically in the regime between kV and MeV. Now, this is true, but depend if the cooling goes very fast, then you can have that actually your composition is frozen at higher temperature. And you might have also some residual reaction below the crystallization temperature, which means two things. The first thing is that the composition can be very different from your 0 temperature 1. And this is an example. So this is the proton and mass number of nuclei for 3 different density, the color code, at 1 MeV. This one component plasma, of course, give you one nucleus. The minimization procedure gives the preferred nucleus. This is the star. If you have an ensemble and you do the minimization of the energy of the system, you don't have one cluster, you have a distribution. And the distribution is given by color code. So you can see here that you don't have one nucleus, but you have many of them. So for each density, you have actually a spread in the Z and A for a given thermodynamic condition. The second thing that it means, if you're at finite temperature, is that you have what people call impurities. So you don't have just one guy, you have many guys. And these guys are called impurity, and typically this coexistence of impurity is recasted in what is called impurity factor. This, which is just a variance in the Z number. This factor typically in cooling simulation is taken as a free parameter. So it's just a number that people adjust on cooling data. And these actually impact dynamical properties of neutron star, as I show here. This is the period versus, the PP dot diagram is one of the first slides I showed with the period of rotation versus the variation of the period with time. These are objects, the crosses and dots, and the lines are simulation. So in this simulation, is assumed that this impurity parameter is small, and then at some point, it can vary. So this yellow one, they assume a QIMP equals 0.1, the green one 10, the blue one 100. So you can see that your prediction varies of order of magnitude according to this parameter. And in this simulation, it's just assumed constant. It's just a value. So I will show you that actually this number is not a constant, and it's really needed to do such multi-component calculation to determine it. This is indeed a result of the composition of the crust. So this, again, the Z and A is a different way to see this figure here for different densities. And you can see that, look at the green. The green is the one component calculation, and the violet is the multi-component calculation. So you see two things. You see that, again, you don't have just one nucleus, you have many. You see that your distribution broaden, this is normal with density. And you also see, and you see even better here at 2 MeV, that you have light nuclei that appear. This is very neutron-rich light nuclei, which means that the one component approximation, which would give you one only cluster, is not adapted to describe properly the crust at finite temperature. And so what this means for this impurity parameter that I told you is so important in simulation. Well, we can already guess it here. This is the variance of Z. So if the distribution increases, we can think that, well, first of all, is not constant, and then it can typically increase with density. And this is what we observe here. So this is for the outer crust. You see it's not constant at all. It's actually a variation of pure resistive and pure conducting layers. And you see here it increases a bit, but then you have the appearance of light cluster. And so the distribution gets very narrow again, and this is why this impurity parameter decreases. Now, at the bottom of the inner crust, you could also have pasta phases, so this could increase again. This remains to be studied, but the main message here is that, first of all, we do need calculation of the impurity parameter throughout the crust, and this is what we have done in a self-consistent way. And this actually impacts transport coefficient and transport properties. And there have been studies, this is an example by Potekin and Chabrier, where you can clearly see that if you have a impurity parameter 0, this is the solid line, or different from 0, you reduce this sigma, that is the electric conductivity, which is intuitively we can understand, because if you have impurity, your conduction is somehow, your conductivity decreases. And this is exactly what we observe here. And this is again a log scale, which means that if we really have a non-constant impurity parameter, we can expect that they could change the transport coefficient that are, and so the transport properties that are important to model cooling. Now, I will stop here. I will leave you with some conclusion. Just to recap, I hope I showed you that nuclear physics input are really needed for neutron-star modeling, with the caveat that, of course, we need to extrapolate data, and so we need theoretical models, that nuclear physics and astrophysics in tandem, they can put constraints on the equation of state, and that all uncertainties, not only in astrophysics, but also in nuclear data, impact astrophysical observation. And of course, we need as microscopic as possible theoretical model when we have no data, but also, of course, experimental data to pin down, to calibrate our model, and of course, astrophysical observation for the high density part. And then I briefly discussed the importance of actually proper treatment at finite temperature, for particularly this has impact for cooling of neutron star. And then I leave here some open questions. One is typically related to the extrapolation from raw data, both experimentally and also observationally, so model dependence of the constraints. that typically what we have from experiment is low density and low temperature. So again, one needs to extrapolate to astro conditions, which is charge neutral system and possibly high temperature and density. And then to really pin down the impact of the microscopic inputs on the astrophysical simulation, we really need to evaluate the propagation of the uncertainty in a controlled way, possibly with systematic studies or Bayesian analysis. And I will stop here, and I thank you for your attention.